In this lesson, we will discuss limits of complex functions. The concept of limits will be very important as we develop the calculus of complex valued functions. So let's begin with our definition of a limit. First, let's let f map the complex numbers to the complex numbers be defined at all points in a deleted neighborhood of complex number z0. Then we're going to define the limit of f of z as z approaches z0 we say that this limit equals w0 denoted by the notation limit f of z as z approaches z0 equals w0. So this notation and this definition means that the point w equals f of z, so the images of z can be made as close to w0 as we like, by taking values of z close to z0. But not equal to z0. So this is analogous to the limit definition in real valued functions. The values of the images f of z are getting closer and closer to the point w0 as z gets closer and closer to the point z0. So since we've already defined distances in the complex plane, we know that the distance between z and z0 can be expressed by absolute values. So this can be expressed by the expression absolute value of z minus z0. So we can give a more precise definition of limits using these distances. So we're saying that z gets closer and closer to z0 implies that f of z is getting closer and closer to w0. This enables us to give a precise definition of limits we say the limit of f of z as z approaches z0 equals w0 if and only if for every positive number epsilon there exists another positive number delta such that the distance from f of z to w0 will be less than epsilon whenever 0 is less than the distance between z and z0, which is less than delta. So this definition says that no matter how small a positive number epsilon you choose, we can find another positive distance delta such that if z is within distance delta of z0 but not equal to z0, then the values of f of z will be within distance epsilon of w0. So let's draw a picture of this definition. So we have z0 in the z-plane, and we have w0 in the w-plane. The idea is if we use the transformation f, we see that if we choose values of z within distance delta of z0, so let's draw a deleted neighborhood around z0, and the distance of this radius would be delta. So if we chose any value of z in this deleted neighborhood of z0, then when we map that value of z, it will be within epsilon neighborhood of w0. So if I draw an epsilon neighborhood around w0, we see that f of z is going to be in this epsilon ball. Complex valued functions are more complicated than real valued functions, because when real valued functions you had to consider limits on a line, on the real line. Now we have to consider values near z0 in a plane getting mapped to values in the w-plane near w0. Let's look at some examples to illustrate this epsilon delta definition of limits. In my first example, I'm going to show that the limit of the real part of z as z approaches z0 will equal the real part of z0. So I'm going to use the epsilon delta definition of limits. So therefore let epsilon be any positive number. Now we're going to have to look at the distances between the real part of z and the real part of z0. So notice that the absolute value of the real part of z minus the real part of z0 can be rewritten as the absolute value of the real part of the quantity z minus z0. And we know that the absolute value of the real part of any complex number is less than or equal to the absolute value of that complex number itself, so we can write this quantity is less than or equal to the absolute value of z minus z0. So we see that the distance from the real part of z to the real part of z0 is always less than or equal to the absolute value of z minus z0, so we can actually choose delta to be equal to epsilon. Therefore, if the absolute value of z minus z0 is greater than 0 and less than delta, then the absolute value of the real part of z minus the real part of z0 will be less than or equal to the absolute value of z minus z0, as we already described, and that will be less than delta, which is equal to epsilon. So this proves the limit. For my next example, I'm going to show that the limit as z approaches 1 minus I of the quantity x plus I 2x times 2x plus y will equal 1 plus I, where I'm assuming that z equals x plus iy. So first let's let epsilon be greater than 0, and we need to decide what we're going to let delta to be to show that this limit is true. So then if the distance from z to 1 minus I can rewrite that as x plus iy minus 1 plus I, and then I'm going to put the real parts together, so I get x minus 1, the quantity, plus I times the quantity y plus 1. So this is z minus 1 minus I, and this will have to be less than delta. Then let's look at the quantity, the distance from x plus I times the quantity 2x plus y and 1 plus I. So we have absolute value of x plus I times 2x plus y minus 1 plus I. And we're going to want to bound this by epsilon, and that'll help us choose what our delta will be. So let's rearrange this term. I'm going to put the real parts and the imaginary parts together again. So this will be the absolute value of x minus 1 plus I times the quantity 2x plus y minus 1. And I already have this bound above where I have the absolute value of x minus 1 plus I times y plus 1. It should be less than delta. So I'm going to try to get that expression isolated in the next line. So I can write this as the absolute value of x minus 1 plus I times y plus 1 and plus I times the quantity 2x. Now I added a plus 1y, so I need to subtract another 1y, so I have a total of minus 2 in this expression to balance the plus 1i here. And now I'm going to use the triangle inequality to break this up, so this should be less than or equal to the absolute value of quantity x minus 1 plus I times y plus 1, which we've already shown is going to be less than delta, plus the absolute value of I times 2x minus 2. So this quantity will be less than delta, and the absolute value of I is 1, and I can pull out a factor of 2 from this expression. So I get delta plus 2 times the quantity, the absolute value of x minus 1. But notice that the absolute value of x minus 1 is equal to the absolute value of the real part of z minus the quantity 1 minus I. So the absolute value of the real part of z minus 1 minus I is x minus 1. So this will be less than or equal to delta plus 2 times the absolute value of z minus the quantity 1 minus I. So this expression will be less than delta plus 2 times delta, which is 3 delta. So we see we started off with this quantity here, and we found that this quantity will be less than the quantity 3 delta, and so therefore if we choose delta equal to epsilon over 3, we'll have that this quantity is less than epsilon, which is what we wanted. So from all this is all kind of like scratch work leading to the final proof. So let's think of this as kind of scratch work. So now the more formal proof, so for epsilon greater than 0, we're going to choose delta equal to epsilon divided by 3. Then from all of our work, we see that if the distance from x plus iy to 1 minus I is less than delta and greater than 0, then the distance from x plus I times 2x plus y to the quantity 1 plus I will be equal to the absolute value of x plus iy minus the quantity 1 minus I plus 2I times quantity x minus 1, and by the triangle inequality, this will be less than or equal to the absolute value of x plus I y minus the quantity 1 minus I plus 2 times the distance from x to 1, and this is going to be less than delta plus 2 delta, which equals 3 delta, which is 3 times epsilon divided by 3, which equals epsilon. And that establishes the limit. Next, we'll show that the limit of z squared as z approaches I equals -1. So again, let's look at our kind of scratch work here. You can think of this as not really part of the finished proof, but it's kind of essential to getting a smooth looking finished proof. So if epsilon is greater than 0, we need to determine the value for delta greater than 0, such that if z minus I is an absolute value less than delta and greater than 0, this will imply that the absolute value of z squared minus -1, so z squared plus 1, will be less than epsilon. But let's look at the quantity absolute value of z squared plus 1. This actually factors, so the absolute value of z squared plus 1 equals the absolute value of z plus I times the absolute value of z minus I, and we're going to let z minus I be less than delta, so let's look at our bound for z plus I. So I can write absolute value of z plus I. If I add and subtract an I from inside, this will be the absolute value of z minus I plus 2I, and by the triangle inequality, this will be less than or equal to the absolute value of z minus I plus the absolute value of 2I. And so if I let z minus I be less than delta, then this quantity will be less than delta plus 2, which is the absolute value of 2I. So then whenever z minus I in absolute value is less than delta, then we will have the absolute value of z squared plus 1 will be that equal to the absolute value of z plus I times the absolute value of z minus I, which will be less than delta plus 2 times delta. So we want this quantity to be less than epsilon. So now let's choose any value of delta greater than 0 such that delta is less than the minimum of 1 and epsilon over 3. So as long as delta is less than 1 and epsilon over 3, then the quantity delta plus 2 times delta will be less than epsilon. So that's the end of the scratch work. Now we can kind of put this all together. So for epsilon greater than 0, let delta be a positive number such that delta is less than minimum of 1 and epsilon over 3. Therefore, if the distance from z to I is greater than 0 and less than delta, then the distance from z squared to minus 1 will be, as we showed, less than delta plus 2 times delta, which now delta is less than 1, so this will be less than 1 plus 2 times delta, which is 3 delta. And since delta is less than epsilon over 3, this quantity will be less than 3 times epsilon over 3, which equals epsilon. Thus, we've demonstrated that the limit of z squared as z approaches I equals -1. Next, we will prove a theorem about the uniqueness of limits. So if the limit of f of z as z approaches z0 exists, then the limit is unique. So for the proof, let's suppose that the limit exists and equals two different values. So suppose the limit of f of z as z approaches z0 equals w0, and the limit also equals w1. So we're going to show that w0 equals w1. So by definition, for every epsilon greater than 0, there exists a delta 0 greater than 0 and delta 1 greater than 0, such that the absolute value of f of z minus w0 will be less than epsilon over 2 whenever z minus z0 and absolute value is less than delta 0 and greater than 0, and the absolute value of f of z minus w1 will be less than epsilon over 2 whenever absolute value of z minus z0 is less than delta 1 and greater than 0. So we're going to choose a delta equal to the smaller of the two delta 0 and delta 1. So let delta equal the minimum of delta 0 and delta 1. Then if z minus z0 and absolute value is less than delta and greater than 0, then the absolute value of w1 minus w0, I can write this, I can add and subtract f of z inside this to equal f of z minus w0 minus the quantity f of z minus w1, and then by the triangle inequality, this will be less than or equal to the absolute value of f of z minus w0 plus the absolute value of f of z minus w1, which is going to be less than epsilon over 2 plus epsilon over 2, which equals epsilon. So now we see that the distance from w1 to w0 will always be less than epsilon for any arbitrary positive value epsilon. So if a quantity is smaller than every positive number, then that quantity must equal 0. So therefore, absolute value of w1 minus w0 equals 0, since it's bounded between 0 and epsilon for any positive value of epsilon. So if the distance from w1 to w0 is 0, we must have that w1 equals w0, and this proves that if the limit of a function of f of z as z approaches 0 exists, then the limit is unique. Now for an important note about limits of complex functions. So if the limit of f of z as z approaches z0 exists, then the symbol, the notation saying that z approaches z0 means that z can approach z0 from any direction in the complex plane. So this means that z can approach z0 from any direction or in any manner. You could spiral in a counterclockwise direction closer and closer to z0, or it could come straight down to z0, or straight from the left or from the right, so in any arbitrary direction, in any direction or any arbitrary manner. So in order for the limit to exist, the limit from every possible direction must all equal the same value for the limit to exist. So recall that in calculus, we had the idea of left-hand and right-hand limits, and we said that the left-hand limit had to exist and the right-hand limit had to exist, and those one-sided limits had to agree in order for the limit to exist. So now, for complex functions, we must consider all possible directions. So if we have z0 in the complex plane, z could come straight down, or z could come in from the right. Z could spiral around and get closer and closer to z0. So we have to consider all possible directions, and all of these limits as z approaches z0 must agree in order for the limit of f of z to exist at z0. Now we'll give an example that emphasizes this point. Let's show that the limit as z approaches 0 of the expression z divided by z bar does not exist. So the way we're going to prove that this limit does not exist is to show that the limit as z approaches 0 from two different directions produces two different values of this limit. And therefore, since limits must be unique, this limit must not exist. So first I'm going to look at the complex plane here, and here's the origin. We're going to let z go to 0 from two different directions. First along the x-axis, and then secondly along the imaginary axis. And we'll show that the limits along the x-axis and the y-axis are different, and therefore the limit does not exist. So z approach 0 along the x-axis. So if z is only approaching along the x-axis, then the complex number z will just equal x. And therefore the limit as z approaches 0 of z over z bar will be equal to the limit as x approaches 0. So this is just a real limit, and z will just be x plus I times 0 over x minus I times 0. And so we see that this just simplifies to the limit as x approaches 0 of x divided by x, but the fraction x divided by x always equals 1. And as x approaches 0, the constant 1 will remain constant, equal to 1. So we see that as z approaches 0 along the x-axis, the limit will equal 1. Now let's let z approach 0 along the y-axis, the imaginary axis. Then the real part of z is 0, so z just equals iy, and the limit as z approaches 0 of z over z bar will equal the limit as y approaches 0 of 0 plus iy over 0 minus iy. And this expression simplifies to the limit as y approaches 0 of y over minus y, which always equals negative 1. And so the limit of negative 1 as y approaches 0 is negative 1. So we see that this can never occur if the limit of z over z bar existed, because you can't have two different limits as z approaches 0 from two different directions. So since a limit is unique, as we just proved, we conclude that this limit does not exist. DNE for does not exist. So it's important to consider limits along any possible path or any possible direction when determining if a limit exists for complex functions. So we're seeing that the concept of limits for complex function mirrors the concept of limits of real functions, and since limits of complex functions are formally the same as those of real functions, we have the same limit laws or limit rules for complex functions. So this next theorem describes these limit laws. Suppose that the limit of f of z as z approaches z0 equals a, and the limit of g of z as z approaches z0 equals b. Then we see that the limit as z approaches z0 of f of z plus g of z will equal a plus b, and likewise the limit of f of z minus g of z will equal a minus b. So we see that the limit of a sum or difference is the sum of the limits, or the difference of the limits. Secondly, the limit of f of z times g of z as z approaches z0 will equal a times b. So the limit of a product will be the product of the limits. Thirdly, the limit as z approaches z0 of f of z divided by g of z will be equal to a divided by b as long as b does not equal 0. So we see that if we want to take the limit of a quotient, we can just take the limit of the numerator divided by the limit of the denominator as long as we're not dividing by 0. Fourthly, so this just follows from the epsilon delta definition of limits, but the limit of any constant will just be equal to that constant c. So for any constant c in the complex plane, the limit of c equals c. Five, the limit as z approaches z0 of a power z to the n will equal z0 to the n. We saw an example of this when we had the limit of z squared as z approached I. We could now just plug in direct substitution for z and get I squared equals -1 for that example. So this is true for any natural number n. So when we combine the limits of constant equal to a constant, the limit of power z to the n equals z0 to the n, and the sum and difference rule, we see that polynomials are just sums and differences and products of these monomial terms. So we see that the limit as z approaches z0 of p of z will equal p of z0 for any polynomial p of z. And final part of this theorem is that the limit of the absolute value of f of z will equal the absolute value of the limit a. So with this theorem in hand, let's evaluate some other limits of polynomials and rational functions. Now let's evaluate the limit as z approaches 1 plus I of the expression z squared minus 2z plus 1. So since this is a polynomial function, we see that we can just do direct substitution and obtain 1 plus I squared minus 2 times 1 plus I plus 1. And if we simplify this, 1 plus I, the quantity squared, will be 1 plus 2I plus I squared, which is minus 1. And then if I distribute a minus 2, I get minus 2 minus 2I and a plus 1. And when we simplify this expression, this will equal negative 1. So we can use direct substitution to evaluate limits of polynomials. What about a rational expression? Let's find the limit as z approaches I of z to the fourth minus 1 divided by z minus I. Well, we can't use part 3 of the previous theorem because if I substitute I in for z, I'll get a 0 in the denominator. But fortunately, the numerator can factor, and we see that z to the fourth minus 1 can be written as z squared plus 1 times z squared minus 1. And then z squared plus 1 factors as z minus I times z plus I. So I have this expression, and we see that since we're not considering values of z equal to I, this fraction will always simplify when z is not equal to I. So I can cancel a z minus I in the numerator and denominator and obtain the limit of the polynomial in the numerator, z plus I times z squared minus 1. And now I can use direct substitution to obtain I plus I times I squared, which is negative 1, minus 1. And this equals I plus I is 2I times minus 2 would give me a minus 4I. Next, we're going to look at limits involving infinity. So in the complex plane, it can be useful to include the point at infinity, which we denote by the sideways 8 looking symbol for infinity. So it can be useful to include the point at infinity with the complex plane. And so if we include infinity, then this is called the extended complex plane. And the extended complex plane will be denoted by a bold C with a subscript for infinity. So this is defined as the complex plane union the point infinity. So we need a way to visualize the extended complex plane so we can describe sets that are in a neighborhood of infinity. So we attribute this next visualization of the extended complex plane to Riemann. So to visualize the extended complex plane, we can think of the complex plane passing through the equator of the unit sphere centered at 0. So the unit sphere would be a sphere with radius 1 centered at the origin, and this visualization is called the Riemann sphere. So imagine here we have the complex plane with the unit sphere centered at the origin, and we have this north pole point, which would be the point directly above 0 on the sphere. So we're going to take any point in the complex plane Z, and we're going to correspond this point with a point on this unit sphere, this Riemann sphere. And the way we're going to do that is by connecting the north pole to Z with a line that passes through the sphere. So as a line joining N and Z passes through the sphere, it passes through at a point which we'll call P. And so in this way we can actually correspond every single point in the complex plane with a point on the sphere. So each Z in the complex plane corresponds to the point P on the sphere, determined by the intersection of the line through Z and the north pole N. The only point in the extended complex plane that we haven't described yet is the point at infinity, and we will identify the north pole N with the point at infinity. So the north pole corresponds to the point at infinity, and we see that this correspondence now gives a one-to-one correspondence between the extended complex plane and points on the Riemann sphere. So this correspondence is called stereographic projection, and we attribute this first to Bernard Riemann. So this correspondence, called stereographic projection, provides a one-to-one correspondence between the Riemann sphere and the extended complex plane. So now with this idea of stereographic projection, we can describe characteristics of epsilon neighborhoods of the point of infinity by recognizing them as neighborhoods of the North Pole on the Riemann sphere. So now let's discuss some definitions of involving limits at infinity. We're going to define the limit of f of z as z approaches z0 to be equal to infinity to be equal to the fact that the limit as z approaches z0 of 1 over f of z will be equal to 0. So if the limit of 1 over f of z equals 0, then we'd say that the limit of f of z equals infinity. Now we say that the limit of f of z as z approaches infinity equals w0 if and only if, in other words, this means that the limit of f of 1 over z as z approaches 0 equals w0. And we will define the limit of f of z as z approaches infinity to be equal to infinity if and only if the limit as z approaches 0 of 1 over f of 1 over z equals 0. So this combines the previous two definitions. So we're actually going to define limits involving infinity in terms of limits involving 0, where we use reciprocals, 1 over f of z or 1 over z, or both. So let's look at some examples using these definitions. First, I'm going to show that the limit as z approaches -1 of iz plus 3 over z plus 1 equals infinity. So to show this, I'm going to show that the limit of the reciprocal is equal to 0 as z approaches -1. So let's evaluate limit as z approaches -1 of the reciprocal z plus 1 over iz plus 3, and by direct substitution I get the limit of the numerator to be equal to -1 plus 1, and the denominator will be -I plus 3, which is non-zero, so this is valid, and since the numerator equals 0, this limit equals 0. This establishes the fact that the limit of iz plus 3 over z plus 1 equals infinity. Next, let's find the limit as z approaches infinity of 3z squared plus z plus 1 over z squared minus I. So this limit if this limit exists, will equal the limit z approaches 0 of the expression 3 times 1 over z squared plus 1 over z plus 1, all divided by 1 over z quantity squared minus I. And if I multiply both the numerator and denominator of this expression by z squared, I get this is equal to the limit as z approaches 0 of 3 plus z squared over 1 minus iz squared. And now I can use direct substitution to obtain the limit 3 plus 0 over 1 minus I times 0, and see that the limit we were trying to show must equal 3. For this next example, I'm going to show that the limit as z approaches infinity of z squared plus 1 over z minus 1 equals infinity. So to simplify the notation, I'm going to write the expression in the limit as f of z. So f of z will be z squared plus 1 over z minus 1. So I need to evaluate the limit as z approaches 0 of 1 over f of 1 over z. So if I take the reciprocal of f and then plug in 1 over z, this will be equal to the limit as z goes to 0 of 1 over z minus 1 divided by 1 over z quantity squared plus 1. Now I see that in the denominator I have a 1 over z squared, so I'm going to multiply both the numerator and denominator by z squared. This will cancel the z's in the denominator, and this is okay because the limit of z squared over z squared is 1. So this simplifies to the limit as z approaches 0 of z minus z squared over 1 plus z squared. And when I substitute in 0, I get 0 minus 0 over 1 plus 0, which equals 0. So by our previous definition, this shows that the limit of f of z as z approaches infinity equals infinity.